Are we starting? Kong, do you allow Prof. Matt to come in? We are starting now? Yeah. But the timing for the next session will be... Yeah. Shall I? No, hold on. Let me, Kong, I need to introduce Prof. Matt first. Yeah. May I start? Very good afternoon, everybody. Today, I'm honored to introduce Professor Matt Santamouris from University New South Wales, Australia. Prof. Matt Santamouris is a Anita Lawrence Professor of High Performance Architecture in University New South Wales, Australia. He is...
Can you see my slide projected? Can you see my slide projected?
Yes, Prof. We can see that.
But now I have projected full screen. Now that I changed the slide, can you see number 2 slide? That's a problem. So when I'm sharing in full screen, it does work.
Mm-hmm. Dr. Maggie, when can I introduce Prof. Matt? I'm a bit confused here. When can I start introducing?
Yes, you see the PowerPoint, but once I change the slides, can you see? Wait. Now I have projected in full screen, and now I'm changing the slide. Can you see number 2 slide?
No.
The problem.
No. But can you go, Prof, to slide number 2 without projecting it?
This is my PowerPoint. Can you see it? Yes, but I like to project it. So this is in full screen. Now it is in full screen, okay? I'm sharing the full screen. Can you see it? So you can see my screen once I project it. Why? Yes, I done it. This is the full screen, isn't it?
Can you, Prof, can you go down there? It's show a screen down there.
I don't know what to do.
Yes, below, down there, nearby the volume, right hand below. Scroll down. Show a screen, full screen. No, down, below.
Now, can you see it in full screen or not? You can. Can you see number 2? I can. Okay. What I can do is to continue, with the non-projected screen, but we will lose all the animations. I don't understand why you can't see. Okay.
All right. Very good afternoon, everybody. I'm honored to introduce Professor Mattheos Santamouris from University New South Wales, Australia. Professor Matt Santamouris is Anita Lawrence Professor of High Performance Architecture in University of NSW in Australia. He is a past professor at the University of Athens, Greece, and visiting professor at the Cyprus Institute Metropolitan University of London, Tokyo Polytechnic University, Bolzano University, Brunel University, and National University of Singapore. He was a past president of the National Center of Renewable Energy Saving of Greece, and he is the editor-in-chief of Energy and Building. He was a previous editor-in-chief of Journal of Advanced Building, editor-in-chief of Energy and Building, Energy Research, associate editor of the Solar
Can
Energy
you see now
Journal of
slide number 2?
Actual or past member of the editorial board of the International Journal of Solar Energy, Journal of
Can you see
Building
my second
Environment,
slide?
Journal of Sustainable Energy, Journal of Low Carbon Technology, Journal of Open Consortium and Building Technology, Sustainable City and
Problem
Society,
solved.
of the Journal of the Ventilation, and he is the editor of the series of book on building, energy, and solar technology, published by the Earth Science and a publisher in London, and editor and author of the 15 international books on topics related to the heat island, solar energy, energy conservation in building, published in Earthscan and Springer. And he is a guest editor of 12 special issues, various scientific journals, scientific coordinator of many
When you are ready,
international
let me
research
know.
programs, and author of 250 scientific papers published in peer-reviewed international scientific journal, and reviewer of research projects in 15 countries of USA, France, UK, Germany, Canada, Sweden, and he is an expert various international research institution and highly cited researcher according to the Claritative in 2017 and 18. I would like to invite Prof. Santamouris to start his presentation.
I can start? Okay, thank you. Good afternoon. Thank you very much for the invitation. The problem of urban overheating is one of the more serious problems of climatic change. According to a very recent study, there are more than 13,000 cities around the world which really face a problem of overheating. And there are about 1.7 billion people under severe overheating conditions. Since 1980 and our days, the number of overheating hours has increased by a factor of 3. And also, actually, there are 118 billion hours of overheating, let's say, all around the globe. So it is perhaps the most serious problem of climatic change. The problem of urban overheating, it is related to the higher temperatures in the center of the cities compared to the surrounding rural and suburban areas. And this is because the thermal balance in the urban environment is, let's say, more positive than in the rural areas because of, let's say, the high absorbed of solar radiation, the blockage of the emitted infrared radiation, the emitted, let's say, anthropogenic heat, and many other reasons. As a result, the temperature in the center of the cities is much higher than in the surrounding areas. Is it a well-documented phenomenon? Yes. There are more than 450 cities, major cities all around the world, where we have data and we have documented the problem of urban overheating. In Asia and Australia, there are more than 110 major cities presenting a serious problem of overheating. And you can see some of them and the magnitude of the overheating. And as you can see, the average magnitude is of the order, is close to 5 degrees of overheating, but there are cities experiencing, let's say, overheating of about 10 or perhaps higher temperature. But it's not just the temperature increase of our cities. Urban overheating is also related to the increase of the duration of hot spells. If really we plot the number of or the duration of hot spells between, let's say, the end of the previous century, I mean the 19th century, and our days, you will see that there's a continuous increase of the number of hours of the hot spells above 37 degrees, or even above 40 degrees. And unfortunately, it's not just that. Also, when really we project the number of heat wave episodes, I mean the frequency of, let's say, heat waves, extreme climatic events, since the beginning of, let's say, the previous century up to our days, you will see that there is a tremendous increase of the frequency, but also of the magnitude of heat waves. So the problem of urban overheating, it is related to the higher temperatures, to the increase of the duration of the hot spells, but also to the increase of the frequency and the magnitude of extreme, let's say, phenomena. Recently, we have found and we have understood that urban overheating is very much related and linked, and there are, let's say, synergies with the global climatic change. During heat waves, the magnitude of urban overheating, of heat, let's say, of the problem of overheating, is increasing tremendously. So there is a very important synergy between the two phenomena. And during, let's say, heat waves, the urban overheating is increasing. And you see in this slide, let's say, the specific details for Sydney is increasing by, let's say, 4 or 5 degrees. So there is a very important synergy between global and regional climatic change. it is evident that higher temperatures, higher duration of hot spells, more higher frequency and magnitude of heat waves will have a tremendous impact on, let's say, our life, especially on energy, health, vulnerability, economy, comfort, pollution. During the very last years, we have really documented very well the impact of urban overheating on the various sectors of our life. And let's start with energy. We know very well that higher temperatures affect very much the supply of, let's say, energy, especially the supply of electricity, but on the other hand, affects very much the consumption of, let's say, energy. It is evident that higher temperature increase the cooling demand of buildings and increase at the same time the peak electricity demand, obliging utilities to build additional power plants. On the other hand, because of the higher temperatures, the efficiency of power plant is decreasing, and at the same time, there is really a much higher risk of power disruption and reduced power, let's say, capacity. Do we have specific, let's say, quantified data to document, the impact of urban overheating on energy? Yes. From a very high number of real data all around the world, we have understood that the global energy penalty of overheating is close to 2.3 kilowatt hours per square meter of city, or if you like, 0.7 kilowatt hours per degree of temperature increase and square meter of the city. Or if you wish to report it per person, it is close to 230 kilowatt hours per person, which is very high, or 78 kilowatt hours per person and degree of temperature increase. So the penalty we are paying because of the urban overheating in average is really very high. And this brings us to the major problem of the future, the increase of the tremendous increase of the energy consumption for cooling. Because of climatic change, because of the increase of the population, because of the increase of the space we are using for, let's say, for living, and because of many other reasons, we expect a tremendous increase of the cooling energy demand. The actual cooling energy demand all around the world is the one shown in the red line in this slide. But once we really project 3 scenarios for the future energy consumption for cooling in 2050, under, let's say, low development scenarios, we expect that by 2050, the demand for cooling will increase up to 320%. Under an average development scenario, this increase may go up to 750%. And under a very high development scenario, the increase of the cooling demand will be of the order of magnitude of 2,270%. When uncertainties are taken into account, the numbers are much, much higher. And this brings us to the major problem of the future, that we will need a tremendous consumption for electricity to satisfy the demand for cooling. Just to understand, the energy consumption for cooling of one simple Indian city, Mumbai, will be much higher than the whole energy consumption for cooling of the United States. So the increase of the cooling demand and the increase of the electricity demand for, let's say, in the third world countries will be a major problem that really has to find solutions regarding the electricity supply, the use of resources, and the pollution issues and the emission issues. But it's not just the energy problem, which is created because of the overheating. Higher temperatures affect very much the environmental quality, and it is the main source of the creation or generation of tropospheric or low-level ozone. More than 87% of the creation of the tropospheric ozone is because of the urban overheating, and it is expected that in the future, this increase of the atmospheric ozone, let's say, will be much higher, and this will create important problems, of health all around the world. But it's not just that. We know very well that because of the urban overheating, the pollutants emitted by, let's say, the power plants increases tremendously. We know very well that for each degree of temperature increase, the CO2 emissions increase by a factor of 3.3%, or the SO2 emissions by 3.35%, or the NOx emissions by 3.6%. So imagine during a day of a heat wave, when temperature is increasing by 10 degrees, that we have almost 35% more pollutants emitted in the atmosphere by the power plants. Apart of the energy and environmental impact of urban overheating, the impact on vulnerable population is extremely important. We know very well that low-income population is living in low, let's say, quality buildings, not protected buildings, and this has a tremendous impact on their life. First, because once they need to use electricity and air conditioning to satisfy the demand and achieve comfort, studies have shown that they have to spend almost 100% more electricity than the average household because of the very bad, let's say, quality of their houses. But unfortunately, most of the houses and most of the households cannot afford to use electricity and air conditioning, and as a result, they live under very high temperature conditions. It is very characteristic that in Sydney, low-income population during, let's say, the summer period, they live under temperatures close to 40 degrees, which is extremely high, and this has a tremendous impact on their, let's say, health. And this brings us to the major issue of urban overheating and the major impact, the impact of overheating on health. This is not something simple. This is very much related to many parameters, and especially socioeconomic parameters, demographic parameters, the health infrastructure in the city, and many other issues. It's not just, let's say, a relation between temperature and, let's say, mortality or morbidity. But recent studies have shown that almost that population living in warmer neighborhoods, in areas where temperature is higher in cities, they have 6% higher risk of mortality compared to those living in cooler urban districts. So there is a very high penalty regarding health and heat-related mortality paid by, let's say, low-income population because of the urban overheating. And this is very clear once we try really to project the relation between temperature and mortality for several, for example, European cities. You see, for example, that this is for Athens, Greece, that that heat-related mortality is increasing almost exponentially once the urban temperature exceeds a threshold close to 32 degrees. Similar, let's say, behavior is for most of the southern European cities, and this shows that really heat-related mortality is increasing in cooling-dominated climates between 28 and 32 degrees. This is not the case in heating-dominated climates, in cold climates, where really the relations between temperature and heat-related mortality is completely different. If we try to project the similar, let's say, curve for London, Stockholm, or northern, let's say, European cities, you will see that heat-related mortality is increasing above 21 to 23 degrees. So higher temperatures and increasing the temperatures may have a tremendous impact on heat-related mortality, even, in, let's say, colder cities. This is very obvious once we try to project heat-related mortality in Sydney. The western part of Sydney suffers from urban overheating because of the proximity to the desert. And the difference between the eastern part, which is, let's say, by the coast, and the western part, which is closer to the, let's say, the desert, is, let's say, up to 10 degrees during the summer period. So in a distance of about 70 kilometers, there is a temperature difference of about 10 degrees. This has really a tremendous impact on heat-related mortality. And you can see from this graph that during, let's say, the summer, heat-related mortality in Western Sydney is up to 3 times higher than, let's say, the heat-related mortality in the eastern part of the city. So this is a major impact that has to be considered. On the other hand, discussing about, let's say, the impact of higher temperatures with the ambient temperature, we have always to take into account that this is very much related to the quality of the dwellings, of the buildings. A recent study has found that the risk factor because of the outdoor overheating is, let's say, close to 6.1 deaths per million, but the combined impact of higher ambient temperatures with bad quality buildings increases by a factor of 3 or 4, up to 23.5 deaths per million. So this means that urban overheating combined with, let's say, low quality buildings may have a tremendous impact on, let's say, health and heat-related mortality. These are the bad news. I try really to present in 15 minutes what really is the impact of urban overheating in our life. What about, let's say, our possibility and our capacity to decrease the temperature of our cities? During the last 15, 20 years, there's a tremendous research that has been taken, undertaken by, let's say, researchers, and we are able really to present and apply, implement mitigation technologies, several types of mitigation technologies that really may help to decrease the temperature of our cities. There are more than 250 large-scale projects all around the world with, let's say, qualified and well-monitored results where really we have very successful implementation of the new mitigation technologies. I don't have the time to go through all the mitigation technologies, but I like to concentrate on the use of, let's say, advanced materials for cooling at the urban scale. And I like to concentrate on 3 technologies that are very promising and are now almost commercialized and offer a tremendous capacity to decrease the temperature of our cities. I will start with the so-called thermochromic technologies. Thermochromic technologies really are related to the capacity of the materials to change their color as a function of the ambient temperature. So once the temperature is low, the material may be of any color, may absorb radiation in order to keep you hot or warm. But during, let's say, the summer period, the materials change their color and became more reflective, as you can see from the specific, let's say, slide. And in this case, they are reflective and really they keep the urban environment and the building cool. These materials have been developed and recent, let's say, testing have shown that once these materials are used in the urban environment, their surface temperature is to about 21 degrees of lower surface temperature than the conventional materials. And if you don't believe me, you can see the thermal graph at the right of this slide, where you can see that the thermochromic materials present a much, much lower surface temperature. These materials are now almost commercialized and may offer tremendous potential for, let's say, mitigation of our cities. However, the major, let's say, improvements and the real revolution on material science has to do with the so-called, the development of the so-called photonic material or radiative cooling materials. These are materials that have been developed and present a very high reflectivity in the solar radiation, more than 97%. And at the same time, these materials, they emit most of the radiation. They emit most of the radiation in the atmospheric window, which means that most of the radiation which is emitted by these materials may escape to the space. So in this case, these materials are really super cool, and recent, let's say, developments and recent measurements we have carried out in, let's say, Australia, in Alice Springs, in the Australian desert, and you see some of the pictures, have really shown that with the development of these materials, we can really depress the temperature of the materials up to 20 degrees below the ambient temperature. Just to understand, while, let's say, the ambient temperature may be 40 degrees, under the sun during the summer, the surface temperature of these materials can be 25 or even lower. So it is a natural air conditioning without the use of any energy that really helps very much to cool the ambient environment. We have applied these photonic materials in a big project of mitigation. We are coordinating in Riyadh, Saudi Arabia, and we have seen that the use of these materials at the urban scale may decrease the peak surface temperature of these materials up to 4 or 5 degrees, which is a tremendous, let's say, potential. These materials, when applied, in areas with heating and cooling demand, I mean that in areas where during the winter there is a need for heating, may increase the need for heating because they are really very cool. So we have developed new modulated technologies which really may decrease the energy consumption and also the surface temperature of the materials up to 15, 20 degrees during the summer, but also may modulate the optical properties of the materials during the winter period, and so the materials may contribute to heating during the winter period. So these materials are win-win materials that really may help to decrease the temperature during the summer up to 4 or 5 degrees and decrease the temperature during the winter up to, let's say, 2 or 3 degrees. The third, let's say, the third family of materials I like to present, it has to do with the so-called fluorescent cooling materials, quantum dots. Quantum dots are nano, let's say, scale materials, which really have a tremendous, let's say, capacity and do not absorb heat. Imagine that, let's say, these materials, when they absorb heat, immediately they re-emit part of the heat as fluorescent, let's say, radiation. In this case, the materials are not really heated. These materials, under specific conditions, may emit more than what it is absorbed. In this case, they may, let's say, decrease their surface temperature tremendously below the ambient one. We have developed mitigation technologies for the urban environment using fluorescent cooling materials, and we have really succeeded to decrease the surface temperature of these materials up to 13 or 14 degrees. Actually, we are carrying out research trying really to develop anti-Stokes materials that emit more than what they absorb. And our expectation is to decrease the surface temperature of these materials up to 30 degrees. So it's a very, let's say, efficient natural air condition without the use of any, let's say, energy. So where we are, we started 15 years ago using reflective materials, and we have decreased the temperature of our cities up to 0.5 degrees. Then, using, let's say, infrared color reflecting materials that they present a very high reflectivity in the infrared sector, we have succeeded to decrease the temperature of cities up to 0.8, 0.9 degrees. Then, we have developed different materials for asphalt, for example, or let's say the new generation of supercool materials, the thermochromic materials, or let's say the quantum dots, the fluorescent materials, or let's say the daytime radiative cooling, the let's say photonic materials. By using these advanced new technology materials, we are able to decrease the peak temperature of cities up to 4 or 5 degrees. In average, this average decrease may be of the order of magnitude of 2 to 2.5 degrees. Actually, there are more than 250 large-scale mitigation projects all around the world, where we have documented a decrease of the peak temperature up to 2.5 degrees. We expect that in the near future, the decrease of the peak temperature may be of the order of magnitude of 3.54 degrees, and with the development of the new, let's say, supercool daytime radiative cooling materials, this may go up to 5 degrees. This may have a tremendous impact on the cooling energy consumption. Simulations that we have carried out for about, let's say, 100,000 buildings in Riyadh using supercool materials have shown that the use of the supercool materials, let's say, under very severe overheating conditions, like in Riyadh, may decrease the energy consumption of buildings up to 25 or 30%. This is a tremendous energy reduction without any cost. But the most important is that the use of these materials, as documented by different projects, may have a tremendous impact on health. In average, we may decrease, by 20% heat-related mortality once we increase the albedo of our cities. And this is documented by several, projects all around the world. So in order to conclude, I have to tell you that actually we are facing a very important problem of overheating. Our cities present an overheating of about 6 to 10 degrees higher temperature, especially during the summer period. This has a tremendous impact on the energy consumption. It increases the energy needs for cooling up to 100%. At the same time, it increases tremendously heat-related mortality up to 300%, and also the peak electricity demand obliging utility to build additional power plants. Research that has been carried out and developments, industrial developments during the very last years has allowed us to develop mitigation technologies that may decrease the ambient temperature, the peak ambient temperature up to 3, 4, or even 5 degrees. This decreases the peak electricity demand up to 10%, which is very important, 10% less power plants, decreases the energy consumption for cooling up to 40%, and also it decreases heat-related mortality up to 40 or 45%. We are confident that in the near future, we'll develop more, advanced material and mitigation technologies to fight overheating. What do we need for the future? Actually, the building sector is, involves very, very various disciplines, people working either on energy or on health or on pollution or vulnerability, economy, comfort, without really taking into account synergies between the different sectors. As a result, we may have good, developments in the field
keynote speech in international conference. Is the recipient of the Best Paper Award of Institute of Physics in 1994. The highlight of the year from Measurement, Science and Technology in 2005. The highlights of the year from the journal Micromechanics and Microengineering, Institute of Physics. MOSET, Measurement, Science and Technology, Institute of Physics, ASME Best Poster Award, ASME International Mechanical Engineering Congress and Exposition. Philips Outstanding Paper Award in ICEPT HDP 2012, Best Paper Award in Second World Congress on Mechanical, Chemical and Material Engineering. Best Paper Award in 4th International Conference on Heat Transfer and Fluid Flow, Fellow of HKIE, and the Distinguished Scientific Achievement Award, the State Scientific and Technological Progress Award, and the Scientific and Technological Achievement Award from the State Education Commission. Okay, let's welcome Professor Chiu.
Okay. Okay. Thank you for the organizer. Thanks for Professor Zhang's invitation. So it is my great pleasure to give the talk today. So I'm Huihe Chiu from the Hong Kong University of Science and Technology. So today I'm going to talk about some of our study for the wearable device for energy efficient in smart green buildings. So I'm going to briefly give an introduction and the wearable sensor in the human in the loop control, and then how to develop this kind of sensors, some key sensors. Okay, so the following figure, this part is our universities. So it's a nice campus. So if you haven't visited our HKUST before, you are welcome to visit us. Wearable device has wide applications. So, for example, this is one example, the general wearable devices. Okay, for different kind of applications. So, to save the time, I'm not going to talk of this one, but the more focus on the buildings. Okay, the buildings, how to use that one. Of course, for the smart building, there's a lot of different kind of sensors, like an infrared beam or different kind of sensor, read, switch, and the pressure, and also a video, ultrasound, Doppler, and so on, the human observations. So some is a commercial available, some is still in the lab, DIY, okay, and the research. So my focus is mainly in the building for thermal comfort and energy saving. So we know thermal comfort depends on many parameters, not just the temperature, right? So in the same environment, can be one person feel very cold and the other person already feel hot, okay, extremely case. So it's a perception of minds, but mainly depends on several parameters, including the air, environmental air, humidity, mean radiant temperature, and the air velocity, now and the closing value, and also the metabolism. Now, this four parameter, air temperature, humidity, mean radiant temperature, air velocity, can be measured easily. But the difficult is the closing value and also the metabolism. So actually my focus for this talk is how to utilize this metabolic sensors, and then use humans' feelings to measure, to adjust this kind of indoor environment. At the same time, to save the energy, okay, save the energy. Of course, the thermal sensation for human being is actually not just affect your thermal comfort, right? So these kind of things, but also affect your productivity. So the study already shown that in the certain conditions, actually the productivity can improve about from the 16 to 26% if you set the right temperature. Okay, of course, this is also have to link with the energy efficient. Now, one example in Hong Kong. So usually people in the summer, they turn on the air conditioner overnight, but on the next day, they get the cold, okay? Because when you fall into sleep, the air conditioning system doesn't know. So they still continue to cool down the air, but when you already fall into sleep, then you don't have to, because your body metabolic rate drop. So you don't have to use so lower temperature to balance the heat loss, right? So at that time, so you feel cold, but you don't know you fall into sleep already. So it's better you have some kind of wearable device, so to detect your metabolic rate, and then know, oh, you are falling into sleep, and then they automatically through the wireless to adjust the air conditioning system to higher temperature. So on the next day, you don't get catch cold, and also you save the electricity, save the energy, right? So this is one example only, okay? One example. Of course, there are many applications, right? There are many applications can be used for, like for young baby. They cannot say, I'm too cold or I'm too hot. So then if you have some kind of wearable device can detect their metabolic rate and then detect their thermal comfort, then they can automatically adjust the environment. Also for elder people, the same. And also for office people and also long distance driver. So this is trying to save this kind of issue. Now just take the Fang's equation model to give some simple example. We may not necessarily have to use the predicted mean for PMV value. Can be other models, but this is just an example. So it means the metabolic rate actually play important role in the important role in the human thermal comfort. Okay, the question is that how to measure this issue, right? So another one is the sensitivity studied by a researcher. So you can see this kind of human thermal comfort sensitivity for air velocity, for humidity usually is always has almost no effect, okay, to this kind of conditions. And then, but you still have other, right? So like, how about the metabolic rate, this one? So they're actually quite sensitive to your thermal comfort. And also, this is a clothing value and and also the air velocity. So this kind of effect, now, as I mentioned before, those 4 factors we can easy to measure, but only the clothing and the metabolism, this is 2 will be difficult. So we are focused on the metabolic rate, okay, the measurement in this talk. So of course, in the thermal comfort, people also consider, can we set some default value? Like if you sit there, so what kind of metabolic rate? If you do the work, cleaning or cooking or something, so the different value. But this is not very accurate, and also depends on individual people. Okay, individual people. Another one is that you can measure it using direct calorimeters. So, but to measure this is accurate, but in reality, it's difficult to do it, right? So you have to measure whole room's conditions. It's not an individual one. And the other one is that you can use the indirect calorimeters. So, but then you have to wear a mask to measure this kind of oxygen consumptions, and then you can convert this one to metabolic rate. But this is nobody want to wear this kind of mask every day, right? So this is not good for people. So can we have some wearable device that can help to estimate the metabolism? Now, smartwatch, these are many types, this kind of smartwatch available in the market, right? So for example, this kind of from Apple Watch, they are mainly optical to measure the heart beating rate and also other oxygen concentration in the blood. Okay, so this one. But they are, and the other type is the accelerometer. Okay, so there are some kind of the gyro sensors, but they are not actually related to metabolic rate directly. Okay, so not related to that one. And then also the other type, optical one, and heart beating rate or other type of smartwatch. So they actually similar. They do the similar, but some they can measure whether they are sleeping or not sleeping. So this is difficult to directly link to this kind of environment control in the building. So for example, there's no at this stage, no one use wearable sensors to directly to control the building environment inside. Okay, so some other type of the wearable device, such as sweating, this kind of sweating rate sensor. This is actually closer to the thermal comfort already. Okay, but it's still not directly linked with the thermal this metabolic rate measurement. Okay, and some other type of sensor. This kind of sensor actually can measure the use of the dynamic wave and so on, can measure the movement, okay, of human being. So this is somehow linked with the accelerometer. Okay, so this, but it's not directly quantitatively linked with the metabolism. The last one actually is what we developed before. So we actually use this one to measure the metabolic rate. We will describe it later. So other type of the non-contact. That's the previous one is a contact. Okay, so that's non-contact. Non-contact this kind of sensor, such as this one use the microwave. Okay, resonators. Okay, so they can actually detect the wrist movement, left, right, and then up and down in this ring. So they can use to locate the position of wrist inside the ring. Okay, so this is one. And the other one is the this kind of energy storage, this kind of system. They actually try to measure the rotation of the relative rotation of the ring with the coil. So they can generate some electronic signals that can detect the wrist rotations. Okay, wrist rotations. So this is a good idea. So, but still not just you can detect the wrist movement, right? Movement. And the third one basically is the detection of the sweat rate sensor. So, but also detected some capacitance or some pulse signals. So they actually try to get some signal, particularly for the pulse. Okay, so so they can measure the heart rate. Okay. Now, in our thinking is that because the thermal comfort for human being is directly the energy balance between the heat generation from the inside the body, so it's from the metabolism, to the heat loss from the skin. So actually in the all these kind of wearable devices, so because they are not for, of course, not for metabolic rate measurement, also not for thermal comfort measurement, but they do not count this kind of heat loss from the skin into, do not count this one. So we think the heat loss probably is one important the factors, in addition to other parameters that we can consider. So then we try to take this heat loss, including the evaporation, convection, radiation, or conduction into account, but still have to integrate this one into the wearable device to measure the heat loss also. So at the end, we try to get some parameter that may affect the thermal comfort, also affect the metabolic rate, okay, the heat loss. So we try to build a very use our microfabrication system, and then to build a small heat loss measurement devices, okay, to build this one. And then we try to integrate this one into the wearable devices, okay. The equation is a simple heat mass balance equations, okay. And then we try to get the heat loss in certain, because temperature, humidity, is all condition you can measure, right? And then what we have to do is that we have a micro fan. This micro fan dry this in this channel, okay, mini channel. So we dry a certain air velocity, and then we can measure this local near skin, this local heat loss. So okay, so we will put this heat loss into consideration when we estimate the metabolic rate. Okay. So another one is the heart rate. Heart rate already used by people for estimate the sports, right? So and also this kind of actually most of the wearable device, they use the heart rate. Okay, use the heart rate. So to estimate some kind of how strong your sport you have and so on. So, but heart rate actually, of course, is very important. We also count this heart rate. Okay, we use the same to heart rate because this actually relate to some kind of energy consumption, oxygen consumption. Okay, so we also consider the heart rate in this condition. Now, what we did is that we consider three things. One is the heat loss, okay, heat loss from the skin. One is the skin resistance or impedance, okay, impedance skin from the skin. And then one is the BMI, but this BMI is a different, it's not a basal metabolic rate, it's a body muscle rate, okay? So this is a BMI value. So we consider this BMI value too. So what's that? So actually, we know actually for human being, this kind of metabolism is actually from where? Actually, is skeleton of muscle, right? So it's from the adenosine triplefit, the APT. There's adenosine ATP, triplefit. This to dry the muscle compression to generate the energy, right? Generate energy. So this one we consider actually we should consider to measure human beings, every people's body muscle rate, and then plus the skin resistance, plus the heat loss. Then we can estimate this total metabolic rate. So this we propose this equation. So this one here. So it's the metabolic rate equals constant time the heat loss, the first term, and the heart rate, and also the BMI value, divided by the skin resistance or impedance. Okay, so this is what we propose according to what we understand the human's structures. So now the question is that how to measure it, right? So we have to build some small system. So one is an aspirating system with a nano fan and a microchannel, and then we use this one, contact to the skin surface, and then this aspirate mainly is to measure the heat loss. And then we, of course, we build in this microcontroller, okay, the old component into integrate to this wearable device. And then also we have a optical one, very small, integrated, very small optical one to measure the heart rate. So this is similar to other wearable device for only for heart rate, okay? And then we also have the skin resistance measurement. So that needs some micro scale electrolyte to contact to the skin, and then to measure this impedance and the resistance. So then after that, we assemble this system together, and then to form the wearable device, okay, for measurement. Of course, now the size is quite big, okay, still not, we are not commercial one. So, and there's still a lot of have to do. And then after that, we use the link this one to the computer, okay, to the computer, and then it can be through the wireless or Bluetooth. Usually we use Bluetooth, and then connect to the computer, and then we can do the experiment. So the experimental work is like this way. Let me see. Oh, at the same time, we actually use the indirect calorimeter mounted to a person's mouth to simultaneously measure the oxygen. Then we do the comparison. One is from the indirect calorimeters, and the other one is from our sensors, wearable sensor, and then try to do the calibration, and also try to do to compare the measurement. Okay, to compare the measurement. Okay, to compare the measurement. We tested the system in our environmental chamber. So this is a Jockey Club controlled environmental chamber. This means this chamber is a computer controlled. You can simulate the indoor, outdoor condition with different air velocity, humidity, radiation, and so on. Okay, so this kind of. And then this is some people, some students actually inside this chamber, and then do the different spots. Okay, from the rest to gradually increase their spot, okay, gradually increase, and then until very high speed. So then we do the comparison of the one is from our model, this one, okay, and the other one is from indirect measurement, indirect calorimeter measurement. So it's correlated quite well. Okay, quite well. It's something the linear relationship. So we can under different conditions, different spots conditions. So we try to use this one. Okay, mainly it's a linear relationship for different kind of temperature and different peoples. Okay, so the correlation factor coefficient is something like 0.88. So of course, still some error. Okay, still we are digging this kind of the uncertainty. So we try to get a better uncertainty. Okay, so I better improve this kind of measurement uncertainty. So try to get the better one. And then the correlation and the different also in the chamber we set a different environmental temperature, right? 22, 25, 28, and so on, different. And then actually the correlation is still quite linear. So we know actually then we think we can use this one to predict the metabolic rate under different conditions. Now this figure is actually we ask the people to from the rest and then suddenly start to go to jump or to run. Okay, so then you can see the metabolic rate suddenly increase, drop, and then ask him suddenly stop, and then he stop, and then this will drop back, right? And the same for this metabolic rate. Okay, this is just the impedance ratio. Okay, so it's a heart rate and impedance ratios. And then the metabolic rate, the behavior measured like this one. So repeatability, if he do the 3 times, is quite well. Okay, repeat is quite well. So it's, you can rest there and then suddenly jump, suddenly run. Okay, so they will go to in this way. Also for this kind of different temperature. Okay, we also set a different temperature, and then we try to do the correlations. Okay, still within certain range. Okay. We also asked some other some people to work in different environment. So means, for example, in the lower temperature condition. So because the lower temperature condition, he actually feel cold if you don't have some sports, right? You don't have activity. So in one condition, so 1 here and 21. So actually, what you calculate the PMV value actually is very low. Okay, so you feel cold. So in that case, actually the environment, the sensor, wearable sensor tell you have to increase the temperature to 26.2. Then he will feel okay, feel comfort. But for the other one, the second condition, he has some strong spot. So then his metabolic rate is high. Okay, heat loss and the metabolic rate is high, and then his temperature can be low. Okay, so it's to make him in the environmental chamber is 15.7. So in the third case, after strong spot and then he come back, so then the temperature has to go high again. So this will tell, this kind of sensor will tell the air conditioning system or environmental chamber automatically tube according to your activity. Okay, according to automatically tube. You don't have to tell people. So this is also for different temperature, 25, 29. So this similar results we get. We also ask different people. Okay, that one is one people, and then different people to do the to do the activity, and then we get a different people has its own different behavior character of the metabolic rate, right? So different people. So it means to me actually each people probably will have to calibrate this one time using the basic called the basal metabolic rate. So everyone basal metabolic rate is depends on his body's character and also the basic heat loss. So this one we have to calibrate this kind of metabolism for individual peoples. So then maybe when you use this device for the first time, you have to calibrate according to this person's body characters. So to calibrate one time, and then you can use. So how to calibrate? I still have no idea, because if you sell this one in the shop, so it's maybe difficult to do the calibration, right? So this is still a question, so we have to answer. We have a different test, many different kind of test. The person actually is more than this one. So then we have a validation group, and then for other people, and then we compare it, this kind of different age, different. But because in the university, most of students is young, okay, young. So we haven't tried for older people and so on. So this is one we can use this one to do this kind of wearable device for the thermal comfort. How many times do I have? Sorry.
Yeah, hello. Yeah, Prof. Yeah, it's about the time.
It's
about 5. You have another five minutes. Yeah.
Oh, Okay, I mean, maybe very quick, go 1 minute. I go through this part, and then I will stop. Okay, so we also one problem here approaches that because for the previous wearable device, we have to use to measure the skin impedance, but the skin impedance usually have to do the contact measurement. Although the other things we can measure non-contact. So we try to use develop impedance capacitance measure to measure the people's this kind of to reduce the capacitance measure to replace the impedance. So this is what we are going to we are starting that. We actually studied that. So we I don't have much time, so I don't talk about this one, but I can show you some results. I can show you some results in this impedance capacitance measure. So actually we build this kind of capacitance sensors like a ring, and then it's 18 this kind of sensors. And then we of course we have to make it beautiful and the people like it to wear. And then you put your waist inside, and then they will detect according to your waist size and the position and so on. They automatically calibrate this, and then they can when you have the activity, your blood vessel will change. Right? The circulation will change. So then they will change the capacitance. So this capacitance change, then we will know how fast of the blood circulation change. This capacitance change, we will use this one to replace the impedance in that model. So this is of course, this kind of accuracy for capacitance is not so accurate like impedance, because impedance measurement is quite precise. But the question is that you have to tie your ring to your waist, so people feel not comfort. But for this ring, it's no capacitance measurement. It's no problem because you just wear it. No matter what kind of position, they automatically can detect your rotation or translation positions. Then you can get the signals. So this is another measure to replace the impedance by integrate this kind of wearable device, okay, to non-contact. So then make people wear this one is more comfort. Okay, so this is what we have done. Okay, for this one, probably I don't go ahead. So maybe the time is up, right? So I just conclude. We developed this wearable sensor, and then for that. So is there any question?
Professor Chiu, is a very nice presentation. I'd like to open the question to the floor. Any question for Professor Chiu? Okay, Professor Chiu, as one question from my side, is there any discrepancy between the men and the women in terms of the
Yes, actually metabolic rate depends on men, women, and also age, means young and old. Okay, so these all are different. So that's why but the basal BMR, basal metabolic rate, this one actually you have to calibrate one time. So when you measure that one, that already reflects the man or the woman or the old people or young people. Okay. It means basal metabolic means your everyone basic metabolism, right?
Okay, I see. So by the way, is it possible for your device being used for the COVID? Yeah, since now the COVID the situation is become worse. then is it possible for your device to do that?
I don't know how can
Yes, because when people talk about this IAQ, the IQ,
I understand. This is indoor air quality, right? But
yes,
this
correct.
one, for for my one, this mainly is the thermal comfort and the energy saving. So we don't consider how good of air, so how clean of the air inside the room.
Okay, yeah, okay, yeah. Thank you, Professor Chiu. Okay, so
Thank you.
yeah.
Thank you for the opportunity to give a talk.
Okay.
Thank you.
Okay, have a nice day.
Okay, bye. Bye. So I can leave, right?
Yeah, you can leave.
I can leave now, right? Oh, yeah. Okay, thank you. Bye.
Okay, thank you all. You can join the oral section that are ongoing at room A and room B. Today, the keynote and the keynote talk are end for today. You can come back tomorrow. Thanks.